In section 12.2, we're going to build on what we learned about matrices. In section 12.1, we talked about how to add, subtract, and apply scalar multiplication to matrices. Now we're going to go even further, and we'll talk about a different type of multiplication, and that's multiplying matrices themselves. Okay, so if we look at this proposition, okay, let A be an M by R matrix and B be an R by N matrix. Essentially what that means is they have different dimensions here. Then the product AB is an M by N matrix given by Cij, where each Cij is the sum of the products of the elements in the ith row of J and the jth column of B. Now again, it sounds very, very complicated, but when we really look at it, it's actually not. So I'm going to illustrate this using an example, and I want you to rely on this illustration to help you understand how matrix multiplication works. So we're going to let A be this matrix. 2, 1, negative 3, 0. We're going to let B be equal to this matrix. Negative 1, 3, 0, and 4. Okay. Now, the way that we're going to multiply, so I'm going to do A times B. So that's this matrix times this matrix. All right, so the way that this is going to work is, and I'll explain more about how to define matrix multiplication, like how it's defined in just a minute. But this product is going to also be, so these two are 2 by 2 matrices. This matrix will also be a 2 by 2 matrix, whatever this product is. So the first thing that I want to do is I want to look at what element am I looking to fill in. If I look at this one, this is the first row and first column. This is the first row, second column. This is the second row, first column, second row, second column. Okay. So the way that this is going to work is that whatever space that you're trying to fill in, you're going to be using the row from the first matrix and the column from the second matrix. Now, what am I going to do with that? I'll give you an example. Here, for this first space, I'm going to take the first row in A and the first column in B. I'm going to multiply each pair of elements, and add them together in order. What does that mean? That means I'm going to multiply these two numbers together. I'm going to multiply these two numbers together, and I'm going to add them up. So that's negative 2 times negative 1, which is negative 2, plus 1 times 0, which is 0. All right? And that ends up being negative 2. All right, and we're gonna repeat that process with each space we're trying to fill in. So for example, here, this is the first row, second column. That means I'm multiplying the first row in the first matrix with the second column in the second matrix. So that's 2 times 3, which is 6, and 1 times 4, which is 4. And that gives me 10. And I'm going to do the same thing, but this time I'm going to use the second row and the first column, then the second row and the second column here. So second row, first column. So second row in A times first column in B. So negative 3 times negative 1 is positive 3. Let me erase that. Yep. Let me go ahead and erase that here. Positive 3. And then 0 times 0 is 0. And that ends up being 3. And then our last space, second row, second column. So second row in A times second column in B. So negative 3 times 3 is negative 9. 0 times 4 is 0. And that just gives me negative 9. And there's my product. Okay? There's my product. Let's try flipping this around, though. Let's try flipping this around. Let's see what happens. I'm just gonna see if I can move my way here. Let's see what happens if I try to do B times A. I want to see if matrix multiplication is commutative. So let's find out. So let's do B times A. So that's negative 1, 0, 3, 4 times 2, 1, negative 3, 0. Okay? 1, 2, 3, 4. So again, here's what I want to do. For each space, multiply the row in the first matrix by the column in the second matrix. So, first row, first column. So this row here times this column right here. So here, this is negative 1 times 2. Negative 1 times 2 is negative 2. 3 times negative 3 is negative 9. And that is negative 11. Okay. Then, I have first row, second column. So first row here, second column here. Negative 1 times 1 is negative 1. 3 times 0 is 0. And that is negative 1. Then I go to the second row. Second row, first column. 2 times 0 is 0, plus 4 times negative 3 is negative 12. Negative 12 here. And lastly, second row, second column. 0 times 1 is 0. 4 times 0 is 0, so I just get 0 here. Now, when I compare these two products, I see that A times B is not the same as B times A. What does this tell me? This tells me that matrix multiplication is not commutative. Now, it has other properties, some of the same other properties that we'll talk about a little bit later, but in general, matrix multiplication is not commutative. I can't do A times B and have it be the same as B times A, right? Especially if they have different matrices. And I'll show you what that means in a second. If you look back here in your notes at the top, look at the original proposition here. A has these dimensions and B has these dimensions. What does that mean? The first thing that we have to check to see before we multiply is to see if the product is defined. And it's only defined, let's see, matrix multiplication is only defined if the number of columns in the first matrix match the number of rows in the second matrix, right? Think of it this way. M and N, we'll call those outer dimensions. And then the R's here we'll call the inner dimensions. To help make it easier to remember. In order for two matrices to be able to be multiplied together, their inner dimensions have to match. Once they match, then the outer dimensions become the dimensions of your product. So I'll give you an example. If I'm multiplying a 3 by 1 matrix times a 1 by 2 matrix, because these match, my matrices becomes a 3 by 2 matrix. My product becomes a 3 by 2 matrix. All right, and things of that nature. Okay, so let me go ahead and give you another example here. All right, let's see. We'll go back over here. All right, here's what we're going to do. We're going to let A be this matrix. 1, 4, negative 3, and 5. We're going to let B be the matrix negative 1, 1. And we're going to let C be equal negative 4, 2, 0, 1, 3, 5. Okay. Before we do anything, we want to make sure that we know what the dimensions of each one of them are. If I look at A, it has 2 rows, 2 columns. So it's a 2 by 2. B has 1 row, 2 columns. So 1 by 2. And C has 2 rows, 1, 2, 3 columns. 2 by 3. Okay. Now, looking at this, trying to figure out what I can multiply, what I can't multiply. Let's get a look at a list of different. Let's look at a list of different products. Let's see. Let's do AB. We'll do BA. We'll do AC, CA, and BC. AC, CA, and BC. Well, the first thing I want to do is I want to check to see which of these is actually defined. Because if it's defined, then I can't multiply. I don't need to worry about it. If I look at A and B, here's A, here's B. So A and B, that's a 2 by 2 and a 1 by 2. Inner dimensions don't match. I can't multiply them. If I look at B times A, so this time B is the first one. 1 by 2 and a 2 by 2. Inner dimensions do match, which means my outer dimensions that means my outer dimensions are going to be the dimensions of this whole product. Okay, so we'll keep that in mind. B times A. All right, A times C. So here's A, 1 by 2 by 2. C is 2 by 3. Inner dimensions match. So my product is going to be a 2 by 3. A, C. C times A. C is 2 by 3. And A is 2 by 2. Inner dimensions don't match. I can't multiply. And then B is a 1 by 2. And then C is a 2 by 3. Check those dimensions out. They check out, which means BC is a 1 by 3 matrix. So BC. All right, so now that I know which now that I know which matrices that I can work with, then I'll go ahead and multiply them out. Let's see, what are my matrices again? A was 1, 4, negative 3, 5. B was negative 1, 1. C was 4, 2, 0, 1, 3, 5. Okay, all right. So, and I'm going to be doing these products: BA, AC, and BC. All right. And as for the other two, we would just say that it's not defined. Okay, and because again, matrix multiplication is only defined when your inner dimensions match, when you line them up next to each other. All right. So B times A, we'll start with that. B times A. So again, the first thing you want to do is you want to make sure that your matrix multiplication is defined with those dimensions. Okay. Then, right. So let's see. B times A. That's negative 1 times 1 times 1, 4, negative 3, and 5. All right. So this is a 1 by 2. This is a 2 by 2, which means that our matrix is also going to be a 1 by 2. 1 row, 2 columns. Okay? So, again, this spot is first row, first column. This spot is first row, second column. So for the first space that I'm filling in, well, there's only 1 row, so I'm using the row here with the first column in B. Okay? So, I'm going to multiply the pairs and add them up. So negative 1 times 1, and then negative 3 times 1, add them together, and I get negative 4. Next up, I have the first row, or the only row, and the second column. Negative 1 times 4, 1 times 5, negative 4 plus 5 is 1. There's my product. And notice that it is a 1 by 2 matrix. Okay. All right, let's do A times C now. So A times C, that's 1, 4, negative 3, 5, times 4, 2, 0, 1, 3, 5. All right, and again, this is a 2 by 2 times a 2 by 3, which means that because these match, our product is also going to be a 2 by 3 matrix. Right? So 2 rows, 3 columns. 1, 2, 3, 1, 2, 3. Okay? So let's start with here. This is first row, first column. So first row in here times first column in here. So that's 1 times 4 is 4. 1 times 4 is 4. So that's 8 in this first element here. First row, second column. First row, second column. 1 times 2 is 2. 4 times 3 is 12. That's 14. Okay. Then first row, third column. First row, third column. 1 times 0 is 0. 4 times 5 is 20. 20. That's first row done. Now we'll go on to the second row. Second row, first column. So second row, first column. Negative 4 times 3 is negative 12. 5 times 1 is 5. Negative 12 plus 5 is negative 7. Second row, second column. Negative 3 times 2 is negative 6. And then 5 times 3 is 15. Negative 6 plus 15 is 9. And then second row, third column. Second row, third column. Negative 3 times 0 is 0. 5 times 5 is 25. 0 plus 25 is 25. And there's my product. And notice it is a 2 by 3 matrix. Okay. The number of columns in this first matrix have to line up with the number of rows in the first matrix. Okay, let's do one more. Let's do B times C. Okay, so that's BC. That's negative 1, 1 times 4, 2, 0, 1, 3, 5. All right, so here I have a 1 by 2. Here I have a 2 by 3. Again, these match, so my dimensions of my product will be 1 by 3. 1 row, 3 columns. 1, 2, 3. All right. So we'll start here. First row, well, again, the only row. First row, first column. First row, first column. Negative 1 times 4 is negative 4. 1 times 1 is 1. Negative 4 plus 1 is 3. All right. Row, second column. Negative 1 times 2 is negative 2. 1 times 3 is 3. Negative 2 plus 3 is 1. And then lastly, negative 1 times 0 is 0. 1 times 5 is 5. 0 plus 5 is 5. And then there is my product. Okay. Again, keep in mind, you can only multiply matrices together if those inner dimensions match up. If they don't match up, can't do it. No matter how much you want to, you can't do it. Okay. So that's how you do matrix multiplication. Last thing I do want to show you. Okay, again, matrix multiplication isn't commutative, at least not all the time. There are very few exceptions. Where matrix multiplication is commutative, but it's rarely ever, even with square matrices, just like the first example that we saw. All right, but they do share some of the same. Properties as addition and subtraction. Like, for example, matrix multiplication can be associative. Now, usually it's associative when it comes to square matrices, meaning it's n 1 by 1, 2 by 2, 3 by 3, and so on and so forth. Just like addition, subtraction, or just addition, multiplication of matrices also has an identity and an inverse. So remember, for addition, I'll write it up here. For addition, the identity is what was it? It was the zero matrix. The identity was the zero matrix, and the inverse was just the opposite of whatever matrix that you had. Whether it's if you have A, then its inverse would be negative A, because they add up together to give me the identity matrix. Matrix multiplication also has an identity and an inverse. Now, the identity is just simply the identity matrix. Now, if you recall, identity matrix is a matrix. It's a square matrix where I have a diagonal of ones from the upper left-hand corner to the lower right-hand corner, and everywhere else is 0. This right here is the identity matrix in for 3 by 3 matrices. I can also do identity matrix for 2 by 2 matrices, which looks like this. Okay, so the identity matrix is an identity property, is the identity for matrix multiplication, and also matrix multiplication does have an inverse. Now we're not going to talk about it in this section, but later on we'll talk about how to find the inverse of a matrix. And again, just like addition, right? It's the matrix where if I multiply them together, I get the identity. Okay. But like I said, we'll talk about inverses at another time. And again, like addition, matrix multiplication has a distributive property. This should be multiplication. Right? So if I multiply, now again, it's not the same as scalar multiplication because again, when you're multiplying matrices, order matters, right? So that means if A is being distributed from the left, then A is going to appear on the left. But if I'm doing this where my matrix is on the right, then my matrix is going to be on the right of each matrix. So with scalar multiplication, it didn't really matter because it was just a real number. But here, I'm multiplying matrices together, okay? I'm multiplying matrices together, which means that whatever side your matrix is on, that's the side that it's going to be when you multiply it into each matrix, or multiply it into each matrix inside the parentheses, okay? And then, of course, you have multiplicative properties of the zero matrix. I don't know why I put A plus 0. I really should just put A times 0 equals 0 times A equals 0. Yeah. So what that basically means is, just like in real numbers, where anything times 0 is 0, any matrix times 0 is also 0 as well. Okay. But again, yeah, like addition, matrix multiplication does have those similar properties.